Hi everyone, my name is Kevin. Welcome to HSC Explained. In this series called Advanced Math Simplified, we're going to go through each of the major topics in the HSC syllabus together and look at number one, how many marks the topic typically relate to. So how much time you should really be spending on studying it. Number two, what is the topic relating to and what do you actually need to know? And three, what are the past exam questions related to this topic? And more importantly, how do we use one systematic way to find out which technique to apply when? And in the future, I also want to share with you, as someone who's represented Australia 3 times in the Asian Pacific Mathematical Olympiad, and also got 99 for Extension 2 Mathematics and 98 for Extension 1, how I create my own system to solve these questions systematically and quickly. In this video, I will explain the conceptual overview of the biggest topic in advanced maths, calculus. Typically, students study this topic last because it's usually perceived to be the hardest topic, but there is good reason why we want to take a look at this first. And I'll try to explain the core concept of this to you in roughly 10 minutes. Firstly, how big of a topic is calculus? From looking at the past exam questions across 4 years from 2020 to 2023, using data from New South Wales Education Standards Authority, calculus accounts for around 1/3 of the whole exam, by far the biggest area. This means if you have a strong grasp of calculus, you're probably most of the way there to passing the exam. There are 4 subtopics, but really everything boils down to 3 core concepts: differentiation, integrations, and limits. Students usually find this to be difficult because there are so many rules and formulae to remember, but the core concepts are actually really simple. Imagine a red car driving down a very long road, and there's an outside observer on the side of the road. The driver of the red car can see the dashboard of the car and how far he's going, let's say 75 km per hour. And this will change every second when the driver accelerates or decelerates. The external observer knows how long the road is, and he has a stopwatch with him. Ultimately, the concept of differentiation is like the external observer is looking at the red car and trying to guess how fast the car is going, kind of like the police officer trying to see if the car is speeding. Another way to say this is the observer is trying to use external information about the road and time to work out what's the speed on the dashboard that the car driver is seeing. And the concept of integration is reversed, is when the car driver, who already knows the speed of the dashboard, is trying to find out how far the car will travel between certain intervals of time. So interestingly, this is something the observer already knows, because if you just tell them, I will start at 10 a.m. and I'll go until 11 a.m., the observer can tell you exactly where your car was and where your car is. And so that's something the observer already knows. So interestingly, differentiation and integration are actually starting from just one of these perspectives, whether you're the red car driver or you're the yellow observer, and you're trying to get information about the other perspective. And the most critical concept that makes this all work is something called limits. All it is trying to say is, if we know that our estimates are infinitely accurate, then our estimates are exactly accurate. So let's break down a bit more using. So remember, in differentiation, with the observer trying to guesstimate how fast the car is going, or what is showing on the dashboard, we're going to start with a very loose guess and will systematically improve the way we're estimating the car speed. We know that speed is distance divided by time, so as a first guess, maybe let's take the car position at 10 a.m. until 11 a.m. and see how far it's moved. So that distance that the car has moved, let's give it a variable. Let's call it delta x1. Now, what is delta? Delta is a triangle looking symbol on the page, and what it signifies is change. So by delta x1, what we really mean is that it's a variable that is relating to the change of x, and x is usually used for position, so how much the car has changed in terms of position in that time. So in a similar spirit, delta t1 is a change of time. And in this particular case, it will be going from 10 a.m. to 11 a.m. So delta t1 will be 1 hour. And that division, delta x1 divided by delta t1, will be our first estimate of what that dashboard is looking at a particular point in time for the red car. And that's really bad. That's a really rough estimate because we're measuring for an hour, but the driver could have accelerated or decelerated 100 times in between. And how do we have confidence that that single point in time is matching with the overall speed? So let's try and improve that estimate by shortening the time gap. Let's say 10 a.m. to 10:30. We can see that that estimate will probably be better than the first estimate in the sense that there's less chances of the driver to accelerate and decelerate, but it's still way too far. But in that particular case, just to illustrate how the variables substitute in, delta T2 will be from 10 a.m. to 10:30, so half an hour. And then delta X2 is the corresponding distance that the car has traveled in that time. So let's keep trying to improve this, and at some point we know that the estimate will be best when the time gap is really small. Let's say 100th of a second. The driver wouldn't have time to accelerate or decelerate, so the average time in that 100th of a second should come really close to how the dashboard is showing. And if we look at the equation, delta Tn is 100th of a second in this case, similar to above, and delta Xn is the distance traveled, and it will also be very close to zero because the car can't move that far in that 100th of a second. But what's this limits part that has a red box next to it? And that limit is trying to say that delta Tn is approaching zero. So it's getting really close to zero, but it's not exactly zero. Note that if it's exactly zero, on the right hand side, the delta Xn on the top should be zero as well, because the car wouldn't have moved in exactly 0 seconds, and time is zero. So it will give you 0 over 0, which is meaningless. Now that limit is very important because it just says it's really close, and when it gets really close, it will approach the instantaneous speed of the car, but not exactly 0 over 0. So that gives you a meaningful result, and that's the whole basis that calculus is built on. And now when you have that limit, that tells you it is as small as you can make it, infinitely close to 0. The left-hand side, which is dx over dt, signifying the differentiation of x with respect to t, and the right-hand side, which is the delta xn divided by delta tn, becomes an exact equal. And this is because of the rule mentioned before. When you're infinitely accurate with your estimate, you can say that is exactly equal, and that's really important. Now, for integration, it's quite similar, but the situation reversed. As the car driver, they might look at the dashboard once to try and guess in an hour how far they've traveled. But let's say they check the dashboard when they just stopped at a traffic light, or maybe they pick a really bad instance of when they're looking at the dashboard, then extrapolate the distance, then that's going to be a very bad estimate. When they, throughout the journey, look at the dashboard a bit more, by the way, don't do this if you're driving, you should be looking at the road, but theoretically, if they look at that dashboard a bit more, their estimate for the distance will be better. The common notation that you'll see for speed is the dash. So for example, x dash here is the rate of change of x, or the speed of x. If you see two dashes, it's the speed of x changing, which is also known as acceleration. So the integral of x dash with respect to t is approximately equal to the sum of x multiplied by t1 from a to b. And here our example would be 10 a.m. and b would be 11 a.m. And on the right hand side, the bottom of the summation would always be 1, and top would be how many times the car driver has checked the dashboard. So in the first estimate, the car driver would have only checked once, so the bottom is 1 and the top is 1. And we'll get more of this when we step through the actual content from the New South Wales Education Standards Authority. Now, with the second estimate, we'll try to improve it a bit more, and you can see that, let's say the driver checks twice, the estimate's a bit better. But again, we know that as we check more and more frequently, we're more likely to get the realistic picture of what happened. So for example, capturing the moment when the driver is accelerating, capturing the moment when the driver is stopping at a red light. When you take all these factors into consideration, you build a very realistic chart of how far the car is actually going in that 1 hour, which is the ultimate goal. So actually, when when you get to estimate n, which is looking at checking the dashboard n times where n is approaching infinity, then that's where you have the exact equal between the left and the right. And that's the technique that would be demonstrated to you of how the car driver would use integration to find out information that only the external observer would have known. Now, these mathematical notations are quite complicated, so don't worry if it's the first time you've seen it, but you don't quite get the symbols right now. The important thing is make sure you understand the core concept of the driver and the observer and how they use this to understand information about the other person, because this will help you think about how to solve the actual exam question. The math notation, symbols, techniques, we'll cover that in the next video, and we'll also give you a systematic way of how to address those in exam situation. Now that you understand the high-level concept of calculus, it's important to look at the specific dot points and structure laid out by the New South Wales Education Standards Authority. As of 2024, there are 4 subtopics. The first subtopic is Introduction to Differentiation, which is covered in Year 11 with 4 dot points: gradients of tangents, difference quotients, derivative function and its graph, and calculating with derivatives. This subtopic is aimed to introduce the topic of derivative or differentiation as a function that defines the rate of change, i.e. speed, if you're looking at the car example from the previous slide, of a given function. And that's a really important concept, and you'll continue to need it a lot in fields of studies in university. The second module onwards is taught in Year 12. And for example, MAC2, differential calculus, consists of only 2 dot points: differentiation of trigonometric, exponential, and logarithmic functions, and the second rules of differentiation. This subtopic is focused on developing your differentiation toolset and also show you how to systematically solve any differentiation problems. The third subtopic aims to use differentiation in practical problems, and finally the fourth subtopic introduces integral calculus. And this is HSC Explained. Hope you enjoyed the video, and see you at the next one where we'll walk through differentiation as gradients of tangents.